OpenStax, Psychology, 2nd edition, Chapter 5, Sensation and Perception. I tend to think of sensation and perception as two sides to the same coin. You really can't have one without the other. When we talk about our sensory systems, we're talking about all of the parts of us that have to deal with giving us information from our environment. Sensation has to do with information coming into our brains. So the sensory receptors are going to be the specific neurons that deal with specific stimuli for specific senses. So, for example, we have auditory receptors, which help us hear. We have olfactory receptors that help us smell, visual receptors that help us to see, etc. And so sensation is literally when that information is coming into those specific sensory receptors. You're probably aware of the 5 senses: vision, audition, which is hearing, olfaction, smell, gustation, taste, and somatosensation, which is touch. But we also consider ourselves to have a few other senses, technically. Your sense of balance is your vestibular sense. Your sense of your body position is proprioception. Your movement is kinesthesia. Your pain is nociception, and temperature is thermoception. For a stimulus to actually register in our brains or to cause an action potential, if you remember back from the biopsych chapter, it first has to be strong enough to be detected, right? With the action potential, we had to make sure that it actually becomes activated. So in cognitive psychology, we refer to that as the absolute threshold, which is the minimum amount of stimulus or stimulation that you need to have to be detected at least half of the time. So, for example, they say on a clear night, your most sensitive sensory cells in your eyes can notice a candle flame, just a tiny little candle flame, 30 miles away. Obviously, the bigger the fire, the further away you have to be, but just a candle flame could be 30 miles away. The just noticeable difference, and incidentally, if you haven't picked this up already, in cognitive psychology, we name things like they are. So the just noticeable difference is the amount of change in a stimulus that's required for you to just notice the difference in the change. See, so just noticeable difference. So it can change depending on the intensity of your stimulus. And so if you opened up your laptop outside at, in the bright sun, you might kind of squint, have trouble seeing the screen. Whereas if you opened up that same laptop in the middle of the night in your room, it would probably be really bright and somewhat blinding, right? So you'll see how there is the stimulus intensity changes in those situations. So if we were talking about just noticeable difference, it's just that minimum increase in brightness required to be noticed. So obviously in a dark room, the just noticeable difference is a lot smaller, whereas in the outside on a sunny day, it's going to be much greater. On the other half of that proverbial coin is perception. Perception has to do with how the brain interprets the information from those sensory receptors. Now, how the brain does that, there's basically 2 kinds of processing. One is called bottom up, which is where the understanding is kind of built from the bottom up, meaning we're starting with all of the little parts and we're trying to figure out what that all means together. The opposite of that would be top down, where basically you already kind of have this idea in your head and it is influencing how you are experiencing the information. We'll have some examples coming up. So again, top down, your previous experience is going to help you recognize or understand this different stimuli, whereas bottom up, you're looking at the details and trying to figure out what they all mean together. I'm going to show you the next slide, hopefully very quickly, and then take it away, and let's see if you can tell what it said. Did you read it correctly? Did you see what it actually said? This is an example of top-down processing. I'm going to guess that half to 2/3 of you missed the second "the." If you don't believe me, you can actually rewind, but it said, flowers bloom in the spring. Now, the reason this is considered top-down processing is that your brain is reading this, it sees the first "the," and it gets to the second "the," and it's like, I know that already. And it ignored the information because in English, we don't generally have two of the same article, the, back to back like that. And so your body, or your mind, I should say, kind of just ignored it. So again, an example of top-down processing. We have a handful of factors that affect our ability to perceive. The first one, we're going to call it sensory adaptation, which basically means that your sense has gotten used to the stimulus, so you don't necessarily notice it anymore. So, for example, when you first go in the ocean, it might seem kind of cold compared to the nice hot beach that you were just standing on. But then once you're in the water for a little while, all of a sudden it doesn't feel all that cold. That's because your sense of touch, or technically your thermoperception, has gotten used to the cold, and so it really isn't paying attention anymore. I have a friend in Honolulu who is a psychologist, which is why this bugs me so much about her. I love her, but this bugs me about her. She understands the concept of sensory adaptation, and yet when she puts on her perfume, she sprays it on enough until she can smell it. Now, she has been wearing this perfume for over 30 years. The same perfume for 30 years. So sensory adaptation probably happened somewhere in the first year. But she'll keep spraying because she thinks she doesn't have enough on until she can smell it, which means that she is somewhat bathed in her perfume, to the point that there are so many scent particles coming from her after that I can often tell, like if I go into a building and she has recently, let's say, been in the elevator and I go in the elevator after her, I can be like, oh yeah, she's here already. And I'm usually right because I can smell that she's there. Again, she should know better. She is a psychologist. Drives me crazy. All right, another one has to do with attention. Basically, if you don't pay attention to it, then your senses aren't necessarily going to register the information. So another way to talk about this is called inattentional blindness. So you aren't noticing something because there's just absolutely no attention being given to it. So I actually just asked my husband if it was okay to tell this story, and he laughed, saying, of course you can tell this story. You should hear all the stories I tell about you, which is probably true. Okay, so we were, let's see, this was probably about 12 years ago, and he was looking in the fridge, and he's like, I can't find, I think it was Parmigiana. I can't find the Parmigiana cheese. And I'm like, it's right there. It should be like right in front of you. And he kept saying it wasn't there. He couldn't find it. So I have to get up and I go over, and sure enough, literally smack right in front of him is the cheese. And so now, whenever he has some sort of inattentional blindness, regardless of what it is, we call it the cheese. And so if he's saying he can't find his sunglasses, for example, he's like, I can't find my sunglasses. Of course, it could just be cheese. Um, Again, he just isn't paying attention, so he doesn't notice it. Another factor is motivation. So if we really want something to happen, then sometimes we keep thinking that we notice it. So I remember many moons ago when I was waiting for my driving test at War Memorial. I had to wait half an hour. It was probably the longest half hour of my life, with the exception of when I got rushed to the OR for the emergency C-section, but that's a different story in a different chapter. Anyway, every single time they said a name, even if the name sounded nothing like mine, I was convinced they had called my name. Why? I was motivated to hear my name because I was insanely nervous and I just totally wanted to get my license. Signal detection theory refers to the change in stimulus detection as a function of your current mental state, right? So that is kind of the theory that explains this change in perception based on motivation. Another thing that can affect how we perceive has to do with our already held beliefs or values or prejudices. So if you think that diet soda tastes horrible and someone tells you that they gave you a diet soda, then you think, oh man, this thing tastes terrible. But in reality, maybe they accidentally gave you an actual full sugared soda, but because you already think that diet soda tastes bad, you automatically thought it was. Another example is some people don't like a particular subject. And so let's say you have math anxiety, for example, so you don't like math, which basically just means you've had bad math experiences in the past. But someone tells you need to take a math class, and you're like, oh man, that's going to stink. And you don't actually know that it's going to, because maybe you're going to have a really awesome math instructor. But you assume, because of all your past experiences where math was really a big struggle for you, that all math classes must be terrible. And another one is life or cultural experiences. How we grow up, what we're exposed to, helps us to see certain things. There's something called the Mueller-Lyer illusion, which I'll show you on the very next slide. That is something that Western people who live in rooms with corners will notice, whereas people who live in round huts, for example, aren't going to notice. So again, with this Mueller-Lyer illusion, if you look in figure A here on the slide, the black lines the black vertical lines, if you look at them, because of the positioning of the blue lines at the edges, most people, at least in Western countries, would say that the line on the right is longer than the line on the left. And that has to do with the fact that when we're looking at, let's say, a wall over here, over in figure B, we know that even though these lines are actually the exact same size, we recognize in our head that even though they might seem the same size, because one is further away, we know that it's actually going to be larger, right? Because the further away something is, and it looks smaller, but in fact it is, a certain size. And so when we apply it to an image like this, it explains why we see the difference. Now, if you grew up in round homes that never had any three-dimensional views like this, then the Mueller-Lyer illusion wouldn't affect you because you had not experienced that. Now, both visual and auditory stimuli occur in waves. And so when we talk about waves, the properties we tend to pay attention to are the amplitude, which is the height of the wave, and the wavelength, which is the distance between either two crests or two tops of a wave, or two troughs or two bottoms of a wave. Now, wavelength is directly related to frequency. Frequency refers to the number of waves that pass a given point in a given time period. One example would be hertz, or it's expressed in hertz. And so longer wavelengths have lower frequencies and shorter wavelengths have higher frequencies. So you'll notice here that the red wave has much longer wavelength and therefore shorter frequency. In other words, we see fewer of them. Whereas the blue wave on the bottom has very high frequencies. We see a lot of them. That's because the wavelengths themselves are short. Now, you've probably heard this before, but we can actually only see a very small portion of the electromagnetic spectrum. So visible light is just this teeny tiny little rainbow that you see here in the colorful bar on the bottom. A lot of the waves are either above or below what we are able to notice. And so, for example, I'm sure there are people here who have gotten sunburnt on a cloudy day. A lot of times we think, oh, it's not very bright outside. We don't need to put sunscreen on. But again, the clouds might be blocking the visible light from getting through, but the ultraviolet light is still able to penetrate the clouds, and that's why you get burnt on a cloudy day. Our brain perceives color by interpreting the lengths of the waves. So if it's longer wavelengths, then we see it more as reds. Kind of intermediate would be green, and shorter wavelengths would be blues and violets. Now remember, the stuff in the middle is the most visible. If it's too long or too short, they're actually harder to see. And so that's actually why, at least in Hawaii, our fire trucks are kind of this yellowish green, or is it a greenish yellow? I can't remember exactly which word goes first. But they're not the classic red that you see on the mainland a lot of times, and that's because people figured out, well, the most visible color in the spectrum is going to be in the middle, which will be those yellowish green colors, and that's why those are the colors of our fire trucks. Now, the amplitude of light has to do with brightness or the intensity of color. So think of that as if you have like a dimmer switch at home. You can turn the dimmer switch really high, making the amplitude or the height of the wavelength really tall, and so then it's really bright light. Or you can make it really dim, which would mean that you have shortened the amplitude or height of the wavelength. Just like the frequency of the light gave us colors, the frequency of sound waves give us pitch. A high frequency is a high-pitched sound, a low frequency is a low-pitched sound. Isn't that a nice, easy way to remember that? And again, humans can only detect or perceive audible sounds between 20 and 2000 hertz. That's why if someone blows, let's say, a dog whistle, we humans can't hear it, but the dogs all start to go crazy, right? Because it is out of, it's above the frequency. It's so high we can't hear it, but the dogs can because they have more sensitive ears. When you talk about amplitude and sound waves, we're talking about loudness. And just like you had the dimmer switch, now you think about your volume knob, right? And so If you turn it all the way up to a higher amplitude, you have louder sounds. If you turn it all the way down, you have lower amplitudes or quieter sounds. So loudness is measured in decibels. The typical conversation is roughly 60 decibels. Your stereotypical rock concert is twice that, so it's like a bunch of yelling. Potential ear damage or hearing damage comes between 80 and 130 decibels. So if you're someone who's attended a lot of rock concerts, or you've ridden motorcycles, or you worked, with loud machinery like jackhammers or airplanes, you have the potential for hearing damage. Now, the threshold for pain for your ears is also 130 decibels. So if it got too loud, it could actually physically cause you pain in your ears. So here's a figure that's also inside your book, and it just shows you the intensity of common sounds. So now we're going to talk a little bit more about vision, or our sense of sight. And for humans and most creatures, our eyes are the sense organ with the sense receptors that take in the information for vision. Now, there are a couple of images in your textbook that show you the anatomy of an eye, or how the visual system works. Instead of trying to memorize the different parts of the eye, I want you to try to focus on understanding how the eye sees. Because if you can do that, then the different parts of the eye are just going to kind of, the details are going to come with it. Okay, so for starters, light waves are transmitted across the cornea, which is this outer layer of the eye, and it enters in through the pupil. Now, the pupil is actually a hole in your eye. It's controlled by the colored part of your eye, which is called the iris. So the iris will either dilate, which is open widely, or constrict, which is shrink down, depending on the amount of light in the room, or if they put some chemical in your eye to get it to do that at the doctor's office. But basically, if the iris says that notices it's really dark, then it's going to try to take in as much of the ambient light, meaning the light just kind of from random things around you, like the clock, or the digital clock, or the street lamp outside at night, and try to take in as much as it can that way. Or if you step outside on a bright day, it will be like, oh, that's too much light. Our eye can't handle that. So the iris is going to constrict and make the pupil really small. And so that's how the light gets through. Again, the pupil is that hole. And then once the light goes through the pupil, it crosses the lens. And the lens, just like you have the lens in a camera, or the lens in a telescope or a microscope, the lens is what focuses the light, and what it focuses it on is the fovea, which is part of the retina. Now, the retina is the back of the eyeball, essentially. And so your fovea is a specific spot on the back of the retina that has the different photoreceptors. Your photoreceptors are connected to what are called retinal ganglion cells. And so the axons from these cells are going to exit through the back of the eye, and they form what's called the optic nerve. Now, this optic nerve then carries that information to your brain. Now, there is the spot on the back of everyone's eye that doesn't have any of these photoreceptors, and so it is called the blind spot. So that's essentially where the information is exiting, right? Because that's where those axons are going out, so there aren't any room for photoreceptors there, and so you technically can't see information if something lands specifically on that spot of your eye. Now here's a much more detailed image of the eye. I don't think we question you to this level in an intro psychology text. If this was an upper level course, like a 300 level cognitive psychology course, you probably would have to know all these details. But for now, the information on the earlier side is plenty. We have two kinds of photoreceptors, cones and rods. And they're named this way because the photoreceptors named cones kind of look like cone-shaped things, so they kind of look like ice cream cones, whereas the rods are just kind of these longer, more evenly shaped kind of, tubes that kind of look like a pipe or something, or, a rod. Okay, so cones we use mostly in the daytime. We call them phototopic vision, or it deals with your phototopic vision. Your cones work best if it's a really well lit room. It's also where you get your color information. A nice little mnemonic device for you would be color and cones, right? So the cones see color, C and C. That will help you remember that. And this is located only in your fovea. Rods are for your nighttime vision or scotopic vision. These work better in low light conditions. They are very sensitive. Your rods are what help you see in really dim light. And they're also involved with your peripheral vision, which of course is the vision on the sides of your eyes, so on each side of your head. And they're located in the periphery of the retina. So again, cones are basically just in the fovea, and the rods are kind of spread out to the edges of the retina. Here is just a picture showing you how the light going into the eye reacts with the rods and the cones. Okay, so we talked about how exiting each eyeball are the axons that create the optic nerve. Now, where these two optic nerves meet, one for each eye, is this kind of X-shaped thing you see in the picture here of the brain, and that is known as the optic chiasm. And the weird thing here is that what happens is that information from the eye, or also known as the right visual field, is sent to the left hemisphere. Information from the left visual field is sent to the right hemisphere. We actually probably talked about this back in the psychobiology chapter, if you remember. Now, once the information has been processed by your occipital lobe, that visual information is going to go through two different pathways. The what pathway will help you figure out what it was you just saw, so that gives you object recognition or identification. And then the where or how pathway kind of tells you location in space, the where, or how you might interact with that particular visual stimulus. We have two major theories of color vision, the trichromatic theory and the opponent process theory. Your trichromatic theory of color vision says that all colors can be produced by combining the colors of red, green, and blue. This is, of course, talking about light. If you're talking about like color pigment, then the colors, the primary colors are red, yellow, and blue. But in talking about light, the primary colors are red, green, and blue. And this applies to the retina, where color vision is controlled by three types of cones that can basically detect these three colors. With the opponent process theory, color is coded into opponent pairs. So black is opposite white, yellow is opposite blue, and green is opposite red. And so with the opponent process theory, some cells are excited by one of the opponent colors and are inhibited by the other. And these apply to the cells after the retina. And so the weird thing is that each theory explains some part of color vision. So there isn't a complete independent theory of color vision that has been accepted by the masses yet. So to support the opponent process theory of color vision, what I want you to do is to stare at the image on the left, which is the American flag, except for the fact that instead of being red, white, and blue, it is green, black, and yellow. I want you to actually stare at the tiny little white dot in the middle of that. And I want you to do that for 30 seconds. Now, I'm not going to keep playing this video and not talk for 30 seconds, so I want you to I want you to pause the video for 30 seconds starting now. Okay, now that 30 seconds has passed, I want you to stare at the little black dot in the middle of the white rectangle on the right hand side, and you should be able to see the flag in the correct colors. If it didn't work for you, maybe try staring at the green, yellow, and black flag again for maybe about a minute. Another thing you can do is perhaps turn up the brightness or amplitude of your monitor to the brighter the screen, the easier this process works. But that red, white, and blue after image, you can see how that works with the opponent process theory. So, you had certain ones, you're staring at the green, yellow, and black, and so then the after image would be in the opposing colors of red, white, and blue. Now here is another example that supports the opponent process theory of color vision. If you stare at the little black plus sign or cross in the middle of the screen, and you look at the colors of the dots that are moving around it, you perhaps see pinkish purplish dots, or perhaps you see a green after image as the pink purple dot disappears. Now, depth perception has to do with our ability to perceive spatial relationships in 3 dimensions. So certain cues in a scene help us to understand or acknowledge a sense of depth. So since most of us are 2-eyed people, there are some people who have only one working eye, but most of us have 2. One of the most common depth cue is our binocular cues. So those are cues that rely on both eyes. So for example, binocular disparity is the concept of the fact that each eye is in a slightly different place on your head, and so it technically sees slightly different views of the world. So that information combined going into your brain and then being perceived by the brain, that slight difference in the 2 visions from each eye, or the vision from each eye, tells your brain how far away something is. Now that basically works up to about 20 feet away. So right now, if you were to hold your thumb maybe 2 inches in front of your nose, and I tell you to stare at your thumb, if you move your thumb away by extending your arm, as you extend your arm out, your eyes that had been turned inward to be able to focus on the very close thumb in front of your face, as your arm extends, those eyes get to go back kind of more straight instead of turning inward, and that's part of your binocular disparity. Now, a monocular cue, or a cue that only needs one eye, there are actually 2 that we can talk about here. Linear perspective. You probably figured this out in like second, third grade when you learned to draw, and to show that the road was going far off into the distance, you learned to converge the 2 lines. And so even though in reality these are parallel lines, like if you drove on the road, it's not like the 2 lines, the 2 sides of the road ever come to a point. It's just that as things get further away, it seems like they're coming together. Another thing has to do with interposition, which is the partial overlap overlap of objects. And so if I have two people in front of me and I can see one person completely, and then the other person I can only see half of them. My brain doesn't say, oh no, there's 1.5 people in front of me. Now what your brain understands is there's two whole people in front of you. It's just that the person in front is covering up or overlapping the person behind them. And so we understand that the person we can see completely must be closer than the person who is only partially visible to us. Now I got a couple of slides here to give you some examples of binocular disparity. The first one, we call it the magical hole in your hand. Okay, so what I want you to do is to find a sheet of paper, and I want you to roll it up into a tube like you're playing pirate when you were a little kid. And you're going to use that rolled up piece of paper like it is a telescope. Okay, what you're going to do is you're going to keep both eyes open. You're going to put your rolled up paper up to one eye. So basically one eye is looking down the tube that's up next to your eye, and then the other one is seeing normally, right? Okay, the next thing I want you to do is I want you to put your other hand, so the hand that's not holding the tube of paper, I want you to put it next to touching the tube of paper, and probably about halfway down the length of the tube, and what you should see is a magic hole in your hand. Now, is there really a hole in your hand? No. What's happening is that one eye is seeing down a tube and the other eye is seeing just kind of normal stuff. But the only way your brain can perceive those two very different images is to make you think you have a hole in your hand. So it's showing that you've got binocular disparity because each eye is seeing something different. Now, if you were not able to follow my explanation, send me a message in La Lima and I will try to explain it again. This next one is called 2 pen points, but it doesn't actually have to be 2 pen points. You can actually use, your pointer finger on each hand, or you can use a pen and the cap of the pen, any two things. Okay, so first of all, put your hands flat down in your lap or on the desk in front of you, either way. Okay, next, with both eyes open, I want you to lift up your hands and touch your fingers together, or the 2 pens together, whatever it is you have. Okay, great. Now shake out your hands again. Now close one eye. So, wink with one eye, but keep that one eye closed. And once again, lift up both hands and try to touch those fingers. Now, about half of you are going to miss. Now, some of you probably got it, but because we actually just practiced it. But some of you are going to miss, and that has to do with the fact that you just lost binocular disparity by closing that second eye. So you only had one eye to give you information. So for some people that throws off their understanding of the depth for your 2 fingers. Our last slide on vision has to do with color blindness. If you are one of the different kinds of color blindness, you are not going to realize that there are actually, in each circle, there's a number. Now, if you don't have color blindness, you can easily look at this and be like 12, 74, 42. You can actually see the numbers. One of my colleagues is colorblind, and he had to actually ask us what the numbers were because he wasn't sure what to say because he couldn't see. I think it was the 2 left ones because he's got a red-green color blindness. Slightly off-topic, silly story for you. I had a friend in graduate school who was colorblind, but they didn't realize that right off the bat, and he almost flunked kindergarten because the teacher was convinced he didn't know the differences in his colors. Luckily, his father was smart enough to say, well, have you checked him for color blindness? And sure enough, he was colorblind. By the way, that was Merlin who said hello. All right, we're moving on to the anatomy of the auditory system, also known as the parts of the ear. All right, so the big cartilagey part we have that, some people stick out more than others, that is officially called the pinna, and it's kind of funneling all the sound towards what is known as the auditory canal. That's the part where you're not supposed to put a Q-tip, like you're supposed to stop and only use the Q-tip on the pinna. If you start going into the auditory canal, you've gone too far. Now, the innermost part of the outer ear, or one could also think of it as just before the middle ear, is what is known as the tympanic membrane. And that sounds travel through the tympanic membrane, which is also a fancy term for your eardrum. Now, just inside the middle ear, we have the three ossicles, or the three smallest bones in the human body: the malleus, the incus, and the stapes. The three more common words for those tiny little bones are the hammer, the anvil, and the stirrup. Now, really, the malleus is closer to more like a club than a hammer, but you get the idea. It's the thing that strikes something, that makes vibrations happen. And so that is the malleus, the incus, and the stapes. Now, your inner ear are made up of the cochlea and the basilar membrane. Basically, the cochlea is this thing that looks like a snail shell or a cinnamon roll. It's all rolled up, and if you were to unroll the cochlea, there would be this layer of hair cells, and these hair cells vibrate based on what happens with the hammer, the anvil, and the stirrup, and that is supposed to be one of the ways that you perceive sound. Here is a slightly more detailed image of the anatomy of your auditory system, or the anatomy of your ear. Only thing I really wanted to point out with this is that within the inner ear we do have fluid, and that fluid is used to kind of, being level. And if you go on a boat, let's say, then all of a sudden that fluid is kind of bouncing up and down. And so for the people who get seasick, you're getting seasick because you're not used to the fluid in your ear moving like that. Auditory transduction, or essentially how you hear, or how you hear sound, or sound waves. So sound waves travel along the auditory canal and strike the tympanic membrane, which makes it vibrate. The vibration causes the three ossicles to move. This presses the stapes into the oval window of the cochlea. The fluid inside the cochlea begin to move, stimulating the hair cells, which are the basilar membrane, right? The sensory receptors for sound. They now become activated, which then sends neural impulses along the auditory nerve, which then basically goes to your brain, and now you've heard sound. We have two different theories of pitch perception, just like we have two different major theories of color vision. So this has to do with how our auditory system can differentiate different pitches. And so one is the temporal theory, which has to do with frequency being coded by the activity level of a sensory neuron. So it has to do with those tiny little hairs on the basilar membrane. Problem with this is that the frequency of action potentials does not account for the full range of what we can hear. The other theory is what's called place theory, meaning different portions of your basilar membrane are sensitive to different kinds of sounds. The bass responds to high frequencies and the tip responds to low frequencies. Both theories are explaining kind of different parts of pitch perception. So just like the different theories of color vision, you kind of need to combine the two theories of pitch perception to fully explain how we hear sound. And just like how we had both monocular and binocular cues for depth perception, we have monaural and binaural cues for sound localization. So with the monaural or one-eared cue, each ear is interacting with different incoming sound waves. With the binaural cues, you got two ears, and they're basically the way that each ear responds to the same sound kind of gives us a sense of localization as well. With the binaural cues, you have the interaural level difference, which has to do with the sound coming from one side of the body being more intense at the closest ears because of the compression or attenuation of the sound wave as it passes through your head. And then you've got the interaural timing difference, which is the teeny tiny difference in time at which a given sound wave arrives at each ear. So it's almost immediate, but not quite. And our ears can tell the difference. Well, really, our brain can interpret the difference from each ear. Oops, said that wrong. Hearing loss refers to deafness, which is either partial or complete inability to hear. You could have congenital deafness, which means you were basically born deaf, or you could have conductive hearing loss, which basically means that for one reason or another, at some point in your life, your ears that used to be able to hear no longer can. And so that can be caused by age, because as you get older, all of our senses start to fail a little. It's why, we need to start wearing glasses as we get older. And we might need hearing aids as we get older. There could also be a genetic predisposition, which just means you were born with genes that basically said that, as you hit a certain age, you're going to start losing your hearing more. And then there is environmental effects. So if you've been exposed to really loud noises, certain illnesses, exposure to certain toxins, all of those can lead to hearing loss. There's also sensory neural hearing loss, which is basically the sensory receptors are working, but something happens between the nerves that have interpreted the sound, or the nerves that have taken in the sound, and the brain's ability to interpret it. So one of the examples of this is what's called Meniere's disease, which has to do with a degeneration of the inner ear structures. And so, maybe it's the basilar membrane falling apart, something like that. But if you have a sensory neural hearing loss, odds are it will be very difficult, if not impossible, to fix, because hearing aids aren't going to make a difference. Before I go on to the next slide, because I saw the term hearing loss, it made me think, that thing that you hear philosophers say about if a tree falls in the forest, does it make a sound? And of course, you're supposed to be debating, whether or not sound can occur without a person being there. Now, I drive my philosophy friends nuts for teaching my students this, but what happens is, if a tree falls in the forest, it produces a sound wave. But a sound is an ear's interpretation of a sound wave. So if there are no ears, whether they're human or animal, to interpret that sound wave, it doesn't technically make a sound, but it did in fact make a sound wave. Now you can go bug people with that. We mentioned these examples of conductive hearing loss earlier, the loud rock music or the sound of a jackhammer. Another thing to think of is if you are wearing headphones. If the person next to you can tell what you're listening to, your music is too loud and you are basically setting yourself up for conductive hearing loss. So I know sometimes it's nice to kind of drown out the rest of the world and make your music nice and loud, but be careful because you don't want to risk future hearing loss. We now move on to our sense of gustation or taste. Basically, we have 6 basic groupings of taste: sweet, salty, sour, bitter, umami, which is the best word I have for this is brothy. It's a Japanese word, I believe. It says it's associated with a taste for MSG, monosodium glutamate. But basically, it's like, if you think of like chicken broth or beef broth, kind of that, I don't know how else to call it, brothy taste. That's another one of your groupings of taste. And then some research now suggests that we possess a taste for the fatty content of food. Fatty foods, to most people, taste pretty good, and that is part of the reason why, at least in the US, we have a lot of overweight people, because we like the taste of fatty foods. Or how I like to say it, like fried things taste good, right? Same basic idea. So we have some sort of a sense of taste for the fatty content of food. Now, how do we take in that taste? It is through our taste buds, which are the little bumpy things on your tongue with little hair-like extensions. Now, they have a life cycle of 10 days to 2 weeks, the individual taste buds, so that, if you accidentally drank something too hot and you burned your tongue, not to worry. Within a couple of weeks, you're going to have new taste buds anyway, so it doesn't really matter. And they say that roughly every 7 years, the kind of arrangement of taste buds on your tongue changes enough that your overall sense of taste kind of changes. And oftentimes that's one of the explanations for why we may not have liked something when we were a kid, but we now like it as an adult. People are like, oh, I must have just matured. Well, kind of. Your taste buds regrouped, essentially, as they kept changing. And now you find that particular stimulus pleasing to your arrangement of taste buds. Now, how do we actually taste? Or what's the transduction? What's the process of tasting? Basically, taste molecules, so the things in your food, bind to these taste buds and cause chemical changes within the cell. And then the information from that is sent to your brain, and you now taste different things. I don't know about you, but I never really wanted to see a tongue close up before. But here is a nice little drawing. You don't have to look at the actual picture on the right there if it kind of weirds you out, like it somehow weirds me out. But your sense of taste, it shows you the taste pore on the taste receptor, which is all kind of below the surface of the tongue. And it, of course, leads to nerves that then send the information to your brain. Your sense of olfaction, or your sense of smell, comes from your nose. Those receptors are within the nose. They're actually on the small little hair-like extensions inside the nose. Kind of similar to how your tongue has taste buds, your nose has these little hair receptors. And so the odor molecules actually bind to the receptors, once again causing some sort of chemical change, and that information is sent to your brain. Now, some people say that smell and taste are related. There's actually a lot of debate on this topic. At the very least, the senses of smell and the sense of smell and the sense of taste, they behave the same way. So there might be similar types of things involved. But whether they're necessarily tied together is best left to, people more into this than me. Okay, we also have pheromones, which are chemical messages sent by another individual. Different species also have these. So, animals would have pheromones. And so it's basically how to communicate information about the reproductive status of your potential mate. So you might have heard that, like, someone who is a woman who is ovulating or who's releasing an egg gives off certain pheromones unintentionally. It's just a thing that happens, which make that woman attractive to a male of the species, because the male is going to be like, ooh, I can keep my genetic line going with that one right now. That's pheromones. We have different types of sensory receptors located in our skin, which help us with different touch-related stimuli. So the sense of touch, there's a few different kinds of things, right? So when we notice pressure or low frequency vibrations, that's Meissner's corpuscles. Whereas Pacinian's corpuscles detect transient pressure and higher frequency vibrations. So transient meaning something that moves or changes. Merkel's discs respond to light pressure. So if you just barely feel something, that would be Merkel's discs responding. And then Ruffini's corpuscles, man, I can't speak today, detect stretch. This is my third time trying to record it, so I'm just kind of like, whatever, we're just going to go with it now. As mentioned earlier, we also have the senses of thermoception and nociception. Thermoception is temperature. I remember when my kid was like a toddler, I really liked holding on to ice cubes. And it was kind of funny because my mom was convinced that there was something wrong with my child because they could hold on to ice cubes, whereas my mother cannot. My mother is more sensitive to the thermoception or extreme thermoception, so like extreme cold or extreme heat, than my child is. And nociception has to do with basically like pain receptors. So this has to do with information going, into the spinal cord directly to the brain. Oftentimes doesn't even, this kind of reaction can happen before you process the sense of pain. So if you have ever accidentally touched something super hot and you'll notice your hand jerks away really fast and then you say ouch, right? It's a nociception reaction. Basically, it's a reflex that your body recognizes the harm, and then a beat later you might notice the pain, right? It takes like a second later for you to go ow, because the signal actually has to then get interpreted by the brain for you to be able to say ow. Now, people who say no pain, no gain, that kind of bugs me. And yes, sure, part of that is that I'm not like, a big bodybuilder type person, but pain is there to protect you, okay? Because if we cause ourselves pain in some way, usually we are doing some type of harm. Now, when you're, let's say, lifting weights and you're causing some pain, you actually are doing harm. You're like ripping apart your muscles, but that's the plan, because you're hoping that they will now scar over and form big muscles, right? That's the idea. Okay, so sorry, went off on a little tangent there. So pain perception is important because it tries to stop us from getting injured. Inflammatory pain means there's some sort of tissue damage. So again, like the lifting weights thing, that's a kind of inflammatory pain. Neuropathic pain has to do with damage to your nervous system. So maybe it's not specifically in, let's say, the muscles or the bone, but it's actually in the nervous system. I know a lot of people who, after either during COVID or when they had COVID or after having COVID, were much more sensitive to neuropathic pain. Why? Because the COVID somehow damaged part of the nervous system, and so it basically messed with the pain cells, the pain receptors, and so things seem to hurt more. Um, One can also have a congenital insensitivity to pain, which is a rare genetic disorder in which you're born without the ability to feel pain. And as someone who suffers from chronic pain, sometimes that sounds really good to me, but at the same time, I don't want to injure myself, so you don't want to have that kind of problem. I mentioned your vestibular sense in an earlier slide talking about your inner ear. So again, your vestibular sense is your sense of balance. Again, it has to do with the fluid-filled part of located next to the cochlea in the inner ear. It's got all this liquid that we're used to having at a relatively steady level. So if we then either start spinning around and making the fluid kind of, whipping around in our ears, or if we're rolling down a hill, same thing, or we're on a boat, our vestibular sense kind of gets messed up. Now, some people, if they've been on a boat long enough, they get used to it, right? That's a kind of sensory adaptation where you're at first you're like, oh, I'm gonna be so seasick because the fluid is just kind of flying in every direction inside your ear, but you get used to it, and then you step off the boat back onto land, and now you can't walk straight on land because you're kind of used to this up and down movement of the ocean waves, and instead we're now on solid ground. And so that's when they talk about needing to get your sea legs, or sorry, your land legs back. That's what they're talking about. There's just a little drawing kind of showing you what I was just talking about, how when our head is upright, how the fluid in the membrane is resting. Whereas if you tilt your head forward, or, because of force of gravity, or again, you're on a boat and things are moving up and down, how things will change. Your senses of proprioception and kinesthesia work with your vestibular system. If you are athletic, whether that's, playing sports, or you are a dancer or a gymnast, odds are you have a good sense of proprioception and good sense of kinesthesia, which is basically talking about understanding your perception of your body's position and how it moves through the space around you. And all this information interacts with your vestibular system and makes you a very fluid or graceful athlete. Okay, we're on our last part about perception. This is the Gestalt principles of perception. You might remember Gestalt from chapter 1. We're talking about the different theories of psychology. Gestalt psychology is a field based on the idea that the whole is different from the sum of its parts. And so something more is happening when we've got everything coming together. And so the different principles involved with Gestalt are the figure-ground relationship, and then we've got the principle of proximity, similarity, continuity, and closure. So the figure-ground relationship, again, these are cognitive psychologists, and so the figure is the thing at which you are looking, and the ground is the background. And so if you are focusing on the white part of the image, perhaps you see a vase, a vase, something like that. Whereas maybe if you are focusing on the darker parts of the image, you see what looks like two people staring at each other. And so that's the difference between figure and ground, and it changes. It can actually go back and forth roughly I want to say it's like every 7 seconds or something, and when you look at different objects. Incidentally, I have a few more figure ground images at the end of this presentation just because I thought they were cool. Okay, the Gestalt principle of proximity, or principle of nearness, which basically says that things that are close to each other tend to be grouped together. Okay, so when you look at the dots in figure A, people will be like, oh yeah, that's just one block of dots. Whereas if you look at the dots in figure B, most people would describe it as three columns of dots, right? Because the um, each of the pairs of dots are closer to each other. So if we were to number the columns, 1, 2, 3, 4, 5, 6 of the six circles, 6 columns of circles, betweens 1 and 2, 3 and 4, and 5 and 6 are closer than between 2 and 3 and 4 and 5. And so, for those reasons, we tend to look at the things that are closer together as units or columns. Next, we have the Gestalt principle of similarity, and this is the idea that things that are alike tend to be grouped together. Now, technically, the proximity or nearness between all of these dots is the same. However, we still would most likely describe this as a row of yellow dots followed by a row of blue dots, and then yellow, then blue, then yellow, then blue, as opposed to saying there are 6 columns, each of which has a yellow, blue, yellow, blue, yellow, blue arrangement of dots. We don't say it that way, right? We say row of yellow, row of blue, etc., etc. That is your principle of similarity. Next, we have the Gestalt principle or law of continuity. And this is the idea that we are more likely to perceive continuous, smooth flowing lines rather than jagged or broken lines. So most likely you would say that these are two curved lines that cross in the middle and make a curved X or a cursive X, as opposed to saying we have two kind of curvy V shape or V shapes that both meet at the points of the V. If I asked you what shapes you see here, odds are you would tell me that on the left there is a circle and on the right there is a rectangle. Well, technically, a circle is a continuous line right around, and a rectangle has 4 solid sides, neither of which these are. But our brain basically fills in the missing pieces of information. That'd be that top-down processing. All of Gestalt is a top-down processing, by the way. We fill in the missing pieces of information, and so we look at this and say, oh yeah, the thing on the left is a circle, the thing on the right is a rectangle. That's your principle or law of closure. Alrighty, so my last slide with words on it, it talks about implicit bias and perception. This is the idea that our perception is influenced by our experiences, our biases, our culture. So there was research done by Dr. Atiba Goff that showed that black boys are considered more responsible for their action than white boys of the same age. You're thinking, why would that be? And that is because people, now admittedly the study was done on university students, and again, students, like we talked about in the earlier chapter for research, students aren't necessarily the best, subject pool to be using. They're not necessarily representative of the all of people, but in this case it was 264 university students, mostly white females, important part, they're involved in the study, and as a group they tended to overestimate the age of black children by over 4.5 years. So a black 12-year-old they thought was 15 or 16 years old, which thus made them seem like they should be more responsible. They also judged black children over the age of 10 as significantly less innocent than white children of the same age. Now, if we were in the middle of a classroom, we'd probably have this great big discussion about what this might say about law enforcement, educational and jury perceptions of defendants of different races. Perhaps you want to talk about that in your journal. We'll see. And like I said, the following slides are a bunch of illusions or illusory figures. I will point out what each one is, and if you have trouble seeing it, once again, just send me a message. What animal do you see here? Is it a duck or is it a rabbit? By the way, if you have trouble seeing what I just said, you might want to hit pause so that it doesn't advance to the next image quite so quickly. Is this book facing towards you or away from you? Or another way to think of it, are you reading the book or are you looking at someone who is reading a book? That tiny little blurred out bottom here makes that image, the figure and ground, flip back and forth on you. What do you see here? Back in the early days when we didn't necessarily refer to other cultures with the greatest respect, this would have been called something else, but instead today we call it the Native American or the Inuit. All right, so you either see the image of a Native American head where the face is looking off towards, it's a profile looking to your left, and the dark is maybe part of the hair or the headdress. Whereas if you see the Inuit, which is someone from a colder climate, you are looking at an entire body, but the person is looking away from you, perhaps in towards a dark room. They're wearing one of those big fuzzy coats that are fur lined, so you could see this kind of fur lining the around the hood and around the arm piece, and yeah, the neck for the Native American would be the feet, or the legs, I should say, the legs of your Inuit. In this image, do you focus on the black figure, which is like a jazz cat saxophonist who's playing his music in, let's say, a smoky bar, and so there's this tiny little puff of smoke kind of in front of the saxophonist, or to the right of the saxophonist in the way we're looking at it, from somebody in the audience? Or is it the kind of the slightly darkened image of a woman's head? How many faces do you see here? The smart aleck answer would be 3, because it's either one wide face with a candlestick in front of the nose, or you've got 2 twins essentially looking directly at each other, facing each other, forehead to forehead. And so you've got the one wide face, the 2 profile pictures there, and so the smart aleck answer is, of course, 3. How old is the presumably female person in this image? You either have a young girl who is looking away from you, and she's got this dainty little nose and a cute little chin, and she's wearing a choker necklace as she looks away from you, and you're seeing the part of the left side of her profile. Or this is an older woman whose chin is on her shoulder, and what is the young girl's ear is the older woman's eye. What is the entire, basically, face of the young girl would be the nose of the older woman. And the choker necklace would be the mouth to the older woman. what do you see here? Students will either yell out a, a skull, because it does look like a skull, or you see a woman sitting at a vanity. A vanity is just a fancy word for a woman sitting at a mirror with a counter with all of her different cosmetic products on the counter. And so basically the corresponds to the left eye of the skull would be the actual woman's head, and the face in the reflection of the mirror would be the skull's right eye. In this final image, what do you see here? It can either be kind of this little hill, or it could be the face of, I believe, Jesus, except he's lying on the ground and looking straight up at the sky.